hoping people are just a little late today, so I'm going to start something that you should not feel like you need to be able to do, but I thought it was kind of interesting from a historical point of view. We talked about the fact that the log of A plus the log of B is the log of AB. And I think I mentioned one time we used this. People who come in afterwards don't know that I just said you don't have to know this, right? Now you do. So how would I go about, using this? This is a table, one page from a book. It's about 20, 30 pages worth. And I'll just try and use this, see if I can make this work. So my first number is 105.15. So I want the integer part of the exponent, that's 2, plus what they call the mantissa, which is the part of the log which is between 0 and 1. And I look on this table here. There it is. My cursor. You look on line 105. 1. Okay, so I see 02160. And then I can see that there's a 5 after it, which is to say it's between 1 and 2 here. And that's an easy interpolation. I look and I see between these two, it's 42. So I want to add 21. And that's the log of this number. This number, well, we're gonna keep the exponent separate. It's minus 2. And then we're gonna look up 10322. 10322. Okay, so now this one here, to get that last digit, let's see, we've got 01368. 01368. And between 368 and the next one, 410, is what? That's 42. So that's where this little table over here, proportional parts, comes in. See, they list 42, and I can see that the last 2 is 8.4. So I'm going to add 8. I don't really have to add 8.4. So 31. Okay. So I want to add these two numbers together. My 2's are going to cancel, which is nice. So I get 0.02181 and 0.01376. Now here's where I actually have to calculate. I have to add, but hopefully everybody's good at adding. So 7, 15, 5, 3, 0. Okay. I know my exponent here is 0, so this is going to be a number between 1 and 10. Now I have to go back. I have to look at my table here. And again, I might have to flip through pages because it might not be on this page, but in this case I think it will. So 03, 557, so I have to kind of look, where is that? Okay, that's between here and here. So my number is 1085, 1.085. And then I can kind of backwards interpolate. How far is 557 from 553? It's 4. And I'm just going to guess, from looking at this table, that's going to give me a 1 here. So I have like a number with 5 significant digits that I multiply by another with 5 significant digits, and I get 5 significant digits. That is to say, I expect there might be some error in the last digit. So those of you who came in late, this is kind of for fun. And so to get rid of some. So these actually were useful before you had a calculator. If you had a slew of numbers you wanted to multiply or divide, you could just figure out their logs, add them up, subtract. You could find square roots by dividing your log in half. That's what we did. Now, you didn't always need quite that much accuracy. And so there was a little handy device that we had called a slide rule. Has anyone seen a slide rule before? Know what they are? Yeah. Kind of had a reputation if you're walking around with a slide rule in your pocket or your, on your belt, you're kind of a nerd, right? It was the stereotype. This is kind of what a slide rule looks like. It's about a foot long, and you notice there's a little stick that kind of slides back and forth with numbers on it. And you notice there are a bunch of scales here. The main scale we would use typically would be the A and B scale, which are both log scales. The idea is you're moving the stick a certain length, you're adding a certain amount, but since it's a log thing, you're actually multiplying. And with a stick like this, you get 3 digits of accuracy, meaning the last digit had some error. But you could do this really fast. You could multiply 5 or 6 numbers, just moving that stick back and forth. This piece here has a hairline on it, just so you can measure up and down and connect the different scales. There also were scales for square root, cube root. There might be for some functions. It's been too long. I don't know what all of these mean, but this is kind of a close-up. And a cheapy one would cost about $5 and it'd be made of plastic. And a really fancy one like this yellow one would be made of aluminum and that would cost $100. So it's like a calculator of the day, except not nearly as easy to use or, yeah. Okay, so I guess that's all that's the entertainment portion today. It's all entertainment, right? Okay. Where did I miss? So we were talking about logs, excuse me for a second here. So let's just to warm up, let's just try one more example here. What we were doing on Wednesday. If I wanted to expand this, how would I do that? How can I expand that using the laws of logs? This is an algebraic expression. I just want to find out how I can break it up into pieces. Yes?
AB log cube root of C.
I'm just repeating what you said. Cube root. Did you say log of C?
Yeah. Log of cube root of C. Yeah.
Log of. Okay. Well, I can't just take this out here. This isn't an exponent. Right?
Would be log AB cube root of C.
Well, okay, let me at least be careful. This is the natural log, but I'll just keep writing that. You can just say log AB, and then.
Cube root of C as the exponent, or would
Well,
be,
it's on the bottom of the division here. I can't just move it up.
so would it be?
L.
Go ahead.
Ln AB minus Ln cube root of C.
Ln AB minus.
Ln cube root of C.
Okay, root of C. All right, that's a good step. Except I keep writing 3 when I mean C. Okay, I can break this up too, couldn't I? What's the Ln of the log of AB? I'm sure you know this, maybe you don't know what I want. I want ln A plus ln B minus ln of, let me write this way, C to the 1/3. Okay, I'm almost done. I want to do one more thing though. What can I do with that 1/3?
Bring it in front of the natural log.
Yeah, 1/3 C. Okay. All right. We have some rules for dealing with logs. All right. The last thing we're going to do in this section, let me propose a question for you. Let's say I had something like this, which I don't really know how to evaluate. I mean, there's no, take a look on your calculator, there's no log to the base 8 button. There's a log to the base E button, there's a log to the base 10 button, but no log to the base 8 button. So I would like to transform this to log, log to the base 10 of something. That way I can use a calculator. So I want to think, how can I do this? And in more general, how can I have some x to the log a, how can I transform that to some other case? All right, well, I'm not sure right away, but let's take a look at something maybe we can kind of use to think about this a little. Let's take the number 256. And I want to express that first as log to the base 2. What would that be? In other words, 256 equals log to the base 2 of what? 16. Okay. Who said that? That was good. In other words, what I'm saying here is, what I'm saying? No. I think I said the wrong thing. I don't think that's true either. Here's what I want to say. What's the log to the base 2 of 256? That's 16. Okay. It was the right answer, it was the wrong question. But you apparently can read minds, right? Okay. So now let's take a look at log to the base 16 of 256. It's not the same thing as my problem, but we want to think about that. That's what? 2, right? And I want to think about what's the relationship between 2 and 16 here. I mean, it might look like it's just this, the reverse, but it's not. I mean, just by mere coincidence, 16 over 2 is 8. And 2 to the 8th equals what? Yeah. I'm going nowhere with this. I'm just confusing you. I'm confusing myself. What are you trying to do? Oh. All right. Well, it's not straightforward at all. Maybe that's why it's hard for students too, right? Okay, let's take a look at how you would figure this one out. Because there is a straightforward method. So let's first just write down a simple statement. I have some base a and some value x, and the log to the base a of x is p. That's an exponent. That is to say, a to the p equals x. Looking at this, I want to take the log of both sides, but to some other base. I want to say the log to the base b of a to the p equals log to the base b of x. Does that seem pretty straightforward? I haven't really, I'm making a statement that a to the p equals x, and I just find the log of both sides to a different base. Okay. Well, I know I can move this p here, right?
So you're multiplying them by log base b, both sides?
No, this isn't a multiplication.
Or you're just giving
I'm taking the function. Maybe if I wrote it this way. I'm applying the log function, right? That's something that looks like this to both sides. Since they're equal, their logs have to be equal. Make that clear? Okay, so now we have p log to the base b of a equals log to the base b of x. They have a lot of variables there. Now would be a good time to maybe eliminate some of them. We can eliminate p because we know from our assumption that p is log to the base a of x. So I'm just going to rewrite this log to the base a of x. This is multiplication. Log to the base b of a equals log to the base b of x. Staring at that, I'm thinking of this. I wanted to express this value, log to the base a of x, as the log to the base b of something. Well, I'm close here, aren't I? I mean, this says if I multiply log to the base a of x times this value, right, which I know, sort of know what it is, then I'm going to get log to the base b of x. That is, I can take log to the base a of x, multiply it by log to the base b of a, and I'm going to get log to the base b of x. Or I could, divide through. There's a lot of logs here and a lot of bases here, so you have to kind of look carefully to get this straight. Okay, that's really what I wanted to do here. Well, if I really want to find out what this value is, how would I do that? Here I've got log to the base b of x, and I'm multiplying it by, or I'm dividing it by a certain value. I'm multiplying it by 1 over the log to the base b of a, right? Log b of x. So if I really want to know what this guy is here, I can now just move this back as an exponent. Right, log to the base b of x to the 1 over log to the base b of a. All right, so depending upon how you write this, I think this is the most common way you're going to find this. This is a way to transform the base of a log. It's a tricky formula. It would do well while you're doing the homework to kind of try and memorize it, or at least see where the symmetry is here. We've got log x, but we're changing the base, so we have to divide by, in this case, a to the base b to get this to become log to the base a of x. All right, that's poorly stated, but let's do an example. Right? do the example I put up. So I have log to the base 8, 5. And I want to change that to something log to the base 10. Okay? So that's going to be log to the base 10 of 5 divided by log to the base 10 of 8. Now, there's a real practical reason for wanting to do that. I have a log to the base 10 button on my calculator. And if I plug these in, I get a number which is about 0.77398. So I go from something I don't have any mechanical way to evaluate, to something I do. This is useful for other things. Okay, that's the change in base formula. Any questions about that? This is kind of important. It's going to come up in homework and elsewhere. Interesting. I just got called by the police. It's not a big deal. A witness to something. All right. Everyone is very silent today. Is there a big party last night that I missed? No? Good guess? Okay, all right. All right. Next topic. Moving along. Oh, I guess this is a good time for me to say something about the exam coming up. That'll get my attention. There's going to be an exam a week from Monday. In theory, it could cover anything from the beginning of time, arithmetic, adding, multiplying, but it could include some of the stuff from the beginning of the class till the first exam, but mostly it'll cover things from where we left off at that exam until what we do today, which is going to be logs. The next subject after logs is the trig functions, which is going to be a big part of the next third of the class. But I'm going to leave, I think, I'm going to leave trig off this exam. So I'll try and come up with another one of those, what could be on the exam fact sheets, things you should know. All right, the next topic, now that we've learned all about exponential functions and log functions, is using them in equations. Evaluating them in equations, figuring out how to solve an equation that has an exponential function or a log function. One thing to keep in mind is the log functions are the inverse of an exponential function. So just as when we had an equation like this, well, what would we we do to unravel this? We would subtract 3 from both sides, because subtraction is the inverse of adding, right? And then we would divide, because division is the inverse of multiplication, right? So we're going to use that same feature of exponential and log functions. They're inverses, so we can kind of undo one with the other when we need to. Okay. If you look at the book makes a big deal out of something, which is not a small deal. The fact that both exponential and log functions are both 1-to-1. And in context, what that means is if you have an expression like this, a to the x equals a to the y, because raising to the power of a is a 1-to-1 function, we know from this immediately that x equals y. And similarly, if you have, log to the base b of x equals log to the base b of y, this is also a 1-to-1 function, so this also implies x equals y. Now, I don't think it's that important to remember that or even understand that. It's kind of useful for higher math to think in terms of, the properties of 1-to-1 functions. The way I look at it is this. I just say, well, let's say I have a to the x equals a to the y. I can certainly do the same thing to both sides of the equation, right? So what would be a good thing to do to an equation that looked like this? Well, I think finding the log to the base a of both sides might be productive. Log to the base a of ax, a to the x, log to the base a of a to the y. Right? I'll take my next step. I'll move my exponents out front. So I have x log to the base a of a equals y log to the base a of a. And at this point, you have two good choices for simplifying this. One is to recognize that this is a constant, so you can divide it out on both sides and you get x equals y. The other is to think about what is log to the base a of a. What is the log to the base a of a? Yes,
It's 1.
it's 1. Yeah. So this is just saying x times 1 equals y times 1. The other side of this works just as well. I have log to the base b of x equals log to the base b of y. Well, if I have, say x equals 3, I can certainly say 5 to the x equals 5 to the 3, right? You can always take equals and raise them as exponents to the same power. That's what I want to do here. I want to say log to the base b of x is an exponent I'm raising b to. And the same thing over here. Well, this one's a little trickier. You have to recognize that here I am taking my function. In this case, my function is the log. And I'm applying the inverse function to it. So what happens when I apply the inverse function to a function? I just get x, right? in this case, the x actually is x. Over here, the x is y. And so this is going to be how we're going to tackle most of these equations. We're going to have to use all the other things we know, about algebraic expressions, but this is the heart of it. Okay. Any questions so far before we start doing real work here? Okay. All right, let's start with something really simple. Have an equation 5 to the x equals 125. Okay, how should I go about solving this? Well, a few different strategies. One is I could note that 5 to the x equals 5. 125 equals 5 cubed. So this, immediately I conclude x equals 3. The other way I might do this, I might look at my original expression and I might say, well, let's find the log to the base 5 of both sides. Log to the base 5 of 5 to the x equals log to the base 5 of 125. Now here I know I can move the x over, and log to the base 5 of 5 is again 1. So this is just x. At this point, I could make that same leap here and realize that log to the base 5 of 125, well, 125 is still 5 cubed. That's log to the base 5 of 5 cubed. Or, again, moving my exponent over, 3 times log to the base 5 of 5. Which, of course, equals 3. I really, the numbers might not be so nice, and I might still want to evaluate this, right? But we learned how to do that just a few minutes ago, right? We know that log to the base 5 of 125 is log to the base 10 of 125 over what? Log to the base... What do I want to divide this by? What kind of log here? What kind of base? 10. And then what's the number? 5. Okay. Something you could punch into your calculator. Which might be what you need to do if you don't have a nice number here. Okay. Let's look at the next level up of complication. What if I said 5 to the 2x equals 5 to the x plus 1? How could I go about that? What would be a good step? We could. Find the log of both sides to what base?
10.
We could. But that would hurt us. Because we didn't really... Do I know how to simplify this in any way? Well, yeah, it would work. It would work. because I can then, move the exponent over log to the base 10 of 5. X plus 1 log to the base 10 of 5. Yeah, that works. And this is a constant that I can get rid of. Okay. So here I have a simple equation, 2x equals x plus 1, or x equals 1. Now, for these types of problems, it's a really good idea to check. Because sometimes you're going to get a phantom solution, one that pops out of your calculation but doesn't work. In this case, we don't have it, but I think it's worth the trouble here. 5 to the 2 times 1 is 2 equals 5 to the 1 plus 1, 2. Clearly, that works. But it won't always. You want to check. All right, that was kind of step 2. We're doing baby steps here. How about this? 3 to the x plus 2 equals 7. Keeping in mind, you want to know what x do I plug in here to make this true? Well, okay, let's go back to, again, how we solve, algebraic problems like this. Again, 2x plus 5 equals 7. We unravel it, right? First we subtract 5, then we divide by 2. To unravel this, we want to get to this x plus 2. What's a good way to do that? What could I do to both sides so I end up with an x plus 2 somewhere? Okay, raise your hand if you're completely lost.
What did you do, a cloud?
Okay. Raise your hand if you're not completely lost but you're feeling sleepy. You didn't drink your coffee this morning.
Wait, I have a question.
And probably didn't drink enough either. Yes, Zoe.
What did you do, I just remember, back when I took this before in high school, my teacher did, this little cloud thing where you just take the top exponent and just drag the 3 over. So,
Yeah, we want to do that, but we can't do that with this expression. We need a log, right?
yeah, you would do that. Oh, wait, you do. Don't you want, you bring the 3 over, you just put the log, and then it's the base 3, and then
Well,
7.
okay.
That'd just be 7.
One thing we could do is we could say, look, if I have an expression like a to the x equals p, that's the same as saying log to the base a of p equals x. So I could do that here. I could say, what's a? A is 3, so log to the base 3 of p, that's 7, equals x plus 2. Okay, that's one way to do it. That's why I made you repeat. Exponential functions. Now, log functions are the inverse function of it. Yeah. So this is just writing the expression using the inverse function. But faced with a problem on a homework assignment or an exam, look at my notes, it's there many times. I want to go right at it, and I look at this and I say, you know what? I'm raising something to 3. I want to undo that. I want to apply the inverse function. The function here is 3 to some value. So I'm going to find the log to the base 3. Okay? Let's just try that. Log to the base 3, 3x plus 2 equals, well, I have to do the same thing here. Ah, now I can, what was that, drag this over here. And now my choice of 3 looks really smart because log to the base 3 of 3, either Stephen can answer. What's log to the base 3 of 3? You're not Stephen. 1. Yeah. So I just have x plus 2 equals log to the base 3 of 7. For now I know x is equal to what? Log to the base 3 is 7 minus 2. If I need to get an approximate number for this, I'm going to have to use that change of base formula. But, you know, as far as giving me an exact answer to the problem, this is it. I mean, let's check. 3 to this thing, log to the base 3, 7 minus 2 plus 2, that's supposed to equal 7. Well, plus and minus 2, right, they go away, right? So now what's 3 raised to the log to the base 3 of 7? Well, again, here I have, I guess I want to do it this way. Here I have this idea that I'm taking a function, I'm raising something, well, I'm finding the log of something to the base 3, a log function. Now I raise that result to the power of 3. I'm using the inverse function. So this is always x, and this, of course, is 7. All right. At baby steps, we're going to take a little bigger step now. We're going to introduce that scary number e. It's not really scary, it's new. Remember when pi was scary? Okay, what if 8 e to the 2x is equal to 20? Okay. What would my first step be here trying to find x? This is really easy. This is real basic algebra.
Divide by 8? Divide by 8?
Yeah, I just divide by 8. Okay, I have e to the 2x, and I can simplify that a little. That's, what is that? 5 over 2. Okay, now I have to do something a little more advanced. What am I going to do now? Yes, Tom? Okay, now, that's exactly correct, but I just want everyone to think for a second, which log? Log to what base?
Is it the natural log?
Yeah, the natural log. So I want to find the natural log of e to the 2x, natural log of 5/2. It's just another base. It's just a weird base, right? Just like this is a weird number to raise something to, or it seems that way at the moment. It won't by the end of this class. Okay, I drag my 2x over here. All right, I want some brave soul to tell me what's the log, the natural log of E. Some brave soul who already doesn't really obviously know the answer one. Thank you. I'm going to help you a little. The log, the natural log to the base E is the log to the base E of E. So what is that?
It's not 1, is it?
Yes, it is 1. Oh, so you guys want to duke it out? You say it's not 1, you say it is 1, right?
Oh, yes, it is.
Or is that a question? Is it not 1? Is it not 1? Yes, it is 1. Sounds very Shakespearean, doesn't it? Is it not 1, sir? Okay. So that's 1. So we just have 2x equals log of 5/2. What do I do with that? Thank you. Divide by 2. And I just say x equals log of 5/2 over 2. We're not going to evaluate this. You could say this is the natural log of 5 minus the natural log of 2. That doesn't really help you any. I mean, you're going to stick it in your calculator and get an approximate value. Either of these will give you the same number. Okay. I'm not going to do the check on this. You might want to think about doing that. All right. This next really is a baby step because we're not doing anything we haven't done. E to the 3 minus 2x equals 4. Okay, by now you should be starting to have kind of a knee-jerk reaction. Of course, my first step is, you know my first step, Kayla? You're thinking you know it, but give her a chance. The worst you could do is say the wrong thing, so don't worry about that. It won't affect your grade or your future in your chosen career position. What have we been doing whenever we see something raised to a power? To unravel it. Okay. Log to the base. Yeah, okay, that's the natural log. Very good, okay? And then, of course, on the other side, we want to find the same thing, right? Okay, by now...
Not the other log. The other log.
The other log?
The LOG one. Not the natural log, the log. Not that.
Okay, so I can still say log to the base E here, that's the natural log, right? You do that here, it doesn't really... remember the other day I was talking about how if you just say log, it depends on which classroom you're in as to what the base is, if you don't specify. So I try not to write log without base. You know, in a science class it would definitely be 10. In a calculus class it's probably E.
So there's E, the LOG.
Well, that's the way to make it really clear. Right? Okay, so move this over here. 3 minus 2x log of E equals log of 4. Oh, natural log of E again. 1. So 3 minus 2x equals log of 4. And from here, I've got pretty simple algebra, right? Minus 2x equals log of 4 minus 3, divided by minus 2 is 3 minus log of 4 over 2. All right.
Would you want us to like actually have a number or just leave the logs?
You would have to, depends on what the problem asks for. The problem asks for an approximate number you picked out with your calculator. You're just going to punch in those numbers into the calculator. I trust everyone can do that, right? You can push a button. Everyone went to the button pushing class today? Yeah, okay. But being at least today more of a math guy than a science guy, I like an exact number. You're not going to be able to write an exact number except like this. All right. I get that feeling. No, we're not that close. We have time to do something hard. Okay? Everybody ready for something hard? All right? Now, in fact, it's not really, you're going to do something you haven't seen before, but you've used all the moving parts, so don't panic. E to the 2x minus e to the x minus 6 equals 0. Uh-oh. Finding the log of this right now is going to do us no good for a number of reasons. To begin with, do not get confused. We know nothing about this. This is not the log of A times the log of B, or the log of A plus the log of B. This is just A plus B. We have to add them, and we find the log. So if we find the log of this side, that's not going to help us any. And log of 0 is what? Log of 0 is undefined. So we need a different strategy. But we look and we see, you know, this is e to the 2x, this is e to the x. E to the 2x is just e to the x squared. So we got something squared minus something minus a constant. To me, that looks like another version of the disguised quadratic. Disguised quadratic. Let me show you what I mean by that. So we know how to solve quadratics. If I set y equals e to the x, and I plug that in here, what do I get? Well, remember this is e to the x squared, so that's just going to be y squared. This is just y. Oh. Now that I can solve. Any suggestions how I can solve that? You gotta be careful, Aaron, when you put your hand up like that, because I think you need to answer. No? Oh, come on. So
You can factor it.
you can factor it. Okay.
It'd be y minus 6 and y plus 1. Or 2. Never mind.
Where's the plus go?
Oh, it goes with the 2.
Okay. So this tells me y is equal to minus 2 or y equals 3. Okay? Well, let me write that out. So e to the x equals 2, or e to the x equals minus 3. Saving time here, we find the natural log of both sides. Right? Okay, so this just becomes x equals the natural log of 2 And this becomes x equals the natural log of minus 3. What's wrong here?
Negative 3 is not
Wrong.
Is it negative 3?
Well, yeah, what's wrong with that?
It's negative.
Can't leave until you figure it out.
Well, I'm gonna leave it anyway.
You got 4 minutes, that's okay. What's the domain? Okay, let's look at the log function. What's the domain of the log function? What values of x am I plugging at? X greater than 0. So negative 3 isn't in the domain, it's undefined. So this is a phantom, it's not even valid, but it's a kind of a phantom solution. If you plug in log of minus 3 here, and you don't pay attention, you might actually get it to come out right. But it does not exist. Or on this subject, what's the range of the log function? All real numbers. All right, it's going to be the opposite of an exponential function. Okay, thank you.